Okay, so we want to determine the displacement at C. We have values for I and E, and we're going to use virtual work, not direct integration. This would be a fairly, we've worked a problem similar to this for conjugate beam. So this would be maybe a little compare and contrast. So let's start by defining the real moment in the structure. I'll need the reactions. So let's find the vertical reaction at A and D. So first I'll sum moments. I'll sum moments about D. Make sure it's in equilibrium. I'm using right-hand rule. So about D, the 16 kip force creates what kind of moment? Positive or negative? Positive. So I got a 16 kip force, and the distance is 30 feet. And then I forgot to label that, sorry. AY creates what kind of moment about D? Positive or negative? Negative. So I would have AY, and it has a moment arm of 40 feet. So what is AY? 12? That's convenient. And then if we sum forces in the y direction, I'll assume up as positive. Then I'll have AY, which acts up. GY also acts up. And the only load in the structure, 16, is acting down. So I should be able to solve for dy. It looks like it's 4 kips. Any questions about that? So, looking at the real loading system, I need to write moment expressions for this. So can I write one moment expression that's valid for the whole structure? No. So I'll have to write one that's good from A to B, the first 10 feet, and then a second one that's good from 10 to 40. So let's start with the first one, which would be valid for the first 10 feet. So I'm making a cut somewhere here. You want to work the left side or the right side? Left. That's a good choice, I think. Probably your path of least resistance. So I'm going to come down here and draw a little free body diagram of that situation. So I have my reaction at A, which is 12, acting up. And I'm going to have the internal bending moment, which I'm assuming to be positive. And that'll be at some distance x. So first we'll sum the moments at this cut surface. And what do we get? Well, the real moment is positive with my sign convention. And the moment due to the applied, well, not applied, the reaction force, 12 kips, is negative. And it has a distance of x. So it looks like the real moment there is just equal to 12x. Now the only place we can check this in the first 10 feet would be at x equals 0, where we know the moment is 0, and this equation does give us that result. Now when we get our other equation for moment on the second side, we can check that at D, and then we can match the two equations to see if we get the same moment at B. So we should have some confidence going ahead that we've got the right moments. So with that said, let's go to the next section. Make a cut somewhere here between 10 and 40. You want to work the left side or the right side? Yeah, I think the right side's a good choice. So I'll come down here and I'll say, okay, from 10 to 40, I want to work the right side. So there's the right piece. I know dy is 4 kips. Here's my internal moment. The distance to the cut is x, And what is the distance of the piece? 40 minus x. Everybody see that? So again, I'll sum moments using right-hand rule as my sign convention. Make sure it's in equilibrium, equal to 0, and start here. So this moment would be negative, the internal moment, and then my 4 kip force would be positive. That's 4 kips times a distance of 40 minus x. So it looks like the moment there is equal to 4 times 40 minus x. Now for this one, it ought to predict the moment at D, and that's at x equal 40. You can see if I put in x equal 40, I get 0. But what would be, let me go back and call this moment 1, moment 2. So moment 1 at x equal 10 should equal the moment from section 2 at x equal 10. So if I put x equal 10 here, I get 120. If I put x equal 10 here, hey, I get 120. So that seems to work. So I feel pretty good about my moment expressions. So any questions about that? So let's now redo this problem, but let's look at the virtual load. So if I redraw my beam, since I want the displacement at C, I'm going to apply my virtual load at C. I'm going to assume it acts down. That means I'm expecting the beam to move down. And then I'll have different reactions at A and B. Since it's right at C, that means I'm 20 feet from A and 20 more feet to D. So it's right in the middle. I'm going to shortcut it a bit and not do the reactions. I think you can probably see that the reactions are just going to be 1/2 and 1/2. If you don't see that, you can quickly do the analysis like we did over here and determine those values. Now you can see I have different ranges for my equations here, right? So for the virtual moment, I'm going to have one equation that's valid from 0 to 20, and a second from 20 to 40. So after I get those equations, I'm going to have to take my real moments and my virtual moments and match them up. But for now, let's just find the virtual moment. So I want to cut this structure somewhere in the first 20 feet. Do you want to work the left side or the right side? Left. You might be seeing a pattern here, which is good. So now this equation will be valid over the first 20 feet. So when I draw my free body diagram for that, I'll have my reaction, which is 1/2, and then internally I'll have the virtual moment. That's the positive sign convention for that at some distance x. So again, I'm going to sum moments at the cut, assume right-hand rule for my sign convention, and then of course make sure everything's in equilibrium. In that case, I have positive moment by my virtual moment and negative moment created by the reaction of 1/2 times the moment arm of x. So it looks like my virtual moment is going to be x over 2. Now, I want to find it from 20 to 40, so I'll make a cut there. Left side or right side? Right side. So this will be good from 20 to 40. And looking at a free body diagram of that structure, with the reaction at the right edge of 1/2, internal moment And of course, the distance to the cut from the left side is x. That means the remaining piece here will be 40 minus x. And we'll do the same thing. So now we'll make sure our structure is in equilibrium. So I'll sum moments about the cut. Make sure it's in equilibrium. So I have that equal to the internal moment here, which is negative. And of course, this 1/2 doesn't look like a half, does it? Is positive with the moment arm of 40 minus x. So my internal moment is 1/2 times 40 minus x. So any questions about that? So now I just have to match them together. So what I'm looking for is the displacement at C is the integral of m real moment divided by the virtual moment over EI. We're integrating in the x direction, and that you'll integrate it over the length. Now in this particular form, you can see that I don't have continuous equations for a moment or virtual moment over the whole length, so I'm going to have to break it up. So how do I do that? Well, let's reevaluate this situation. So I had a real moment that was good from 0 to 10. Do I have a virtual moment that's good from 0 to 10? Sure. I have one that is good from 0 to 20, so it's good to 10. So that means I can integrate from 0 to 10. So now the next one I have to start at 10. How far can I go? Well, the real moment can start at 10 and go all the way to 40. My virtual moment can start at 10 and have to, got to stop at 20. See that? Because it's going to change. So that means I've got to stop this one at 20. So I got to pick up where I left off. I can't leave anything off. So 20. So starting at 20, do I have a moment equation that's good from 20 to the end? I do. Do I have a virtual moment that's good from 20 to the end? I do. So I can go all the way to 40 there. That's a really nice characteristic of integrals, is that you can divide them up in any way you want, as long as you don't leave any segments out or overlap them, and there's no loss. This is an equal sign, not an approximation. So now I just have to plug all my stuff back into that. They all have EI as a constant, so I'm just going to pull that out front. So the first one's going to be the integral from 0 to 10 of my real moment, which is 12x, times my virtual moment from 0 to 10, which is x over 2. Do I see that? Now I go to the next one, which is an integral from, 10 to 20. This isn't good from 10 to 20, is it? But this one is 4 times 40 minus x. So this will be 4 times 40 minus x. That's my real moment. What's my virtual moment from 10 to 20? Still x over 2. And then my final integration from 20 to 40. What's my real moment from 20 to 40? It's still this. 4 times 40 minus x. And my virtual moment from 20 to 40, well, that's the second one I computed, which is this one. 1/2 40 minus x. and then I'll close that up. So that's the point in the problem where I would say what? Enough. I'm done. Right? And that's probably where you get left off on the second exam. Now, if you really like this kind of stuff, by the way, that would be very tedious to do. That might take you 5 or 10 minutes just to check it 2 or 3 times to make sure you got the right answer. Now, if you only have 15 minutes to do the problem, not a good use of your time. For me, that's good, though. You've shown all the skill and technique that I'm interested in. The rest is just busy work. On the homework, though, not an issue. You have to crank it out. And that's what mastering engineering will require. So what I'll do today is I'll stop here, but I'll go back to my office and do the calculation out on this paper, and I'll put that on the website, but this won't be in the video. So you'll have access to this if you want. Any questions about that? Well, we're going to work a few more of these. Okay.